Good day to you all. My name is Fraser White and I am Product Marketing Manager for Rigaku's single crystal products. And I'd like to thank you all for joining us for another TOPIQ webinar. We hope you're all well and staying safe. Today's webinar is perhaps one of the most relevant to all of us as researchers during this pandemic. We'll get going shortly, but first I'd like to remind you to use the Q&A button at the bottom of your screen if you'd like to ask questions rather than the chat window, as we may not see them there. At the end of the presentation, we'll read out and answer as many questions as we can, time permitting. Also, watch out for the polls throughout the presentation, as we'll be asking some questions as we go along. So please allow me to introduce our presenter for today, Dr. Joe Ferrara, who is our Chief Scientific Officer and Deputy Director of our X-ray Research Laboratory. Joe will be giving us a presentation on what to do when the lights go out. So Joe, please take it away when you're ready.
Thank you, Fraser. I'm going to go ahead and stop my video and just focus on the slides. And so to begin with, I'd like to announce the Rigaku School for Practical Crystallography, which will be holding June 1 through 5th and June 8th through 12th for 1 hour each day from 9 to 10 Central Time. This is designed to help mitigate the loss of some of the crystallography courses that have been canceled for the summer. We realize it's not a full course, but we hope to provide some training for many younger crystallographers. You can register for this at the Rigaku website. You can go directly to this link or just go to www.rigaku.com, go to support and select upcoming webinars, where you'll also find a number of other webinars that we'll be holding between now and June 1st. There will be more after June 1st, of course. And then you can also view past webinars by selecting the past webinars tab. So we will be recording this webinar. It is being recorded as I speak. A copy of the webinar will be available and you'll receive an email with the download. If you have any difficulty viewing the webinar, of course, you can download it. You can send us questions during the presentation. You'll see a Q&A button that looks like this at the bottom of your screen. We'll address the questions at the end of the presentation. As Fraser mentioned, we won't be monitoring the raise hand function. He will be looking at the chat window to see if there are any issues relevant to the talk, like, for example, my audio goes out or the video goes out. The first poll that we're going to ask is about the Rigaku X-ray forum. If you haven't joined, please do. Fraser?
So I've just launched the poll. So hopefully you can see on your screens just now that we're asking the question, are you a member of the X-ray forum? So I'll give you approximately a minute to answer this. And if everyone answers before then I'll let you know and stop the poll. But we're interested to know this to see if people are communicating with us through the forum or other means.
You can also answer anonymously if you don't want to be identified. Oh, there are a few more. Looks like we've reached the top of the curve.
Yeah, so shall we stop there?
Sure. Thank you.
Okay, I'll share the results as well.
So it looks like about 58% of you are a member of the forum and 42% haven't joined yet. I would strongly suggest joining at some point. Okay, moving along. I always like to acknowledge my colleagues first, just in case I run out of time. So Mark Del Campo did a lot of the protein data collections that I'll talk about. Pierre, Takashi, Matthias, Fraser, and Akihito were also helpful with producing a number of the slides. Fraser produced a lot of the graphics for many of the slides. Thank you, Fraser. So as an introduction, what to do when you can't collect data at your favorite ring. So here, as I mentioned in the abstract, we're going to look at the latest technologies to fill the gap in missing beam time and help maintain throughput for various projects in the Homelab. We'll also see how protein and small molecule hardware have converged, allowing you to leverage investments in one unit for both types of samples. And so what we'll do is look at advances in detector technology, goniometer, source, automation, and software. So we're kind of working our way backwards from the X-ray source, or from the detector backwards to the X-ray source. So our second poll, and there's actually only 3 of them in total, will be now, where Fraser will ask what you think about future changes in synchrotron usage.
So with the COVID pandemic, I've launched the poll, so if you can't see it, please let us know in the chat window. With the pandemic, we're wondering if you're going to change the way you view using the synchrotron afterwards. So maybe you have some significant part of your research depending on the synchrotron. Maybe you don't, so we'd like to know how you're using it and how you plan to use it in the future. So I'll give you another 30 seconds or so to answer.
So this is useful information. It's looking, you know, even though statistics is a small number, about a third will change, a third won't change, and a third might change.
Yeah.
Very ambiguous. I think we can end it, Fraser.
Yeah, okay.
Thank you. And you can share it. So those are the final results. About as evenly split as you can get. All right. Thank you. Okay, so first I wanted to show you something. This is something that Mark Del Campo did. So with 2 minutes of data collection on a XtaLAB Synergy Custom system with a Micromax 007HF and a VHF optic, tuned down to about 6 milliradians of divergence, using 3 scans of data in 2 minutes total. He was able to take a lysozyme crystal and create these very beautiful maps through SAD phasing. Just an example of the kind of experiment you can do now. Very high quality data very quickly in the home lab. So this experiment was done with a HiPix detector. The HiPix 6000 is our first detector for single crystal diffraction. It is a scintillator-free photon counting detector with 2 digital photon counting for unparalleled sensitivity. It provides a very high dynamic range, an adjustable signal threshold, and we'll talk about that feature later on, a pixel size of 100 microns, and a maximum readout speed of 100 hertz in 0 dead time mode. So what are the important features of a hybrid photon counting detector? Well, first and foremost, photon counting. We provide true direct detection, X-ray photon counting, which enables near noiseless measurement. This is not just about providing or approximating photon counts, it's real photon counts. Counting means digitally registering each photon as a count when it arrives. Direct detection is required to count photons as scintillator generates omnidirectional, lower energy photons, and are thus harder to detect as visible photons. From a visible photon measurement, i.e. with a scintillator, the number of incident X-ray photons can be estimated. So on the next slide, we'll see this graphically. Here we have, my mouse is not working right. 1 second. Here we have the photon counting setup. Each photon generates a signal in a charge shaping amplifier and then is discriminated against a threshold. And so we have individual spikes here where a photon comes in and a noise floor which is significantly lower than each spike. The counter is incremented as each photon arrives and there's no opportunity for dark current buildup. And once the count is registered, it's stored digitally, and at that point, there is no noise in the system. With an integrating or detector with a scintillator, you accumulate all the signal as you're accumulating the data, the important signal as well. So you accumulate background, dark current, read noise, and so all that has to be then subtracted out, which by in and of itself adds noise to the measurement. So moving along, Some of the other important features of an HPC detector include low detector noise. Noise is random in nature, and it makes it very difficult to subtract cleanly. Therefore, you're adding noise by removing dark current and read noise. Weak signals are most affected by the noise, leading to inaccurate weak intensities. And unlike other technologies, a true photon detector adds no noise at this step. So important features, again, pixel size. So a large pixel produces a signal that's spread out over the pixels. And so these individual events get merged into pair of reflections that are indistinguishable or difficult to distinguish. When you have smaller pixels with a sharp point spread function, remember an HPC has a top hat point spread function, these individual events are not spread out as much, and so they can actually be detected as events in single pixels, or if it crosses a pixel, in just 2 pixels. Another important feature is the ability to collect at shorter distances, which improves the number of orders that can be resolved across the detector. For those of you that used image plates years ago, the general rule of thumb was 1 millimeter per angstrom of unit cell length. With an HPC like ARC, it's possible to collect at distances as small as 1/3 the maximum cell length to collect data. Small pixels gives much higher spatial resolution, while the point spread function ensures peak separation, as we saw on the previous slide. With beam divergence control, even very large protein cells can be studied at surprisingly close distances. And so direct detection is shown here. We have the integrating detector with indirect detection. X-ray photon comes in, passes through a beryllium window that reduces the signal, gets absorbed by the scintillator, producing a Lambertian source. So there are actually lots of photons coming out in all different directions. Some may have a reflective barrier here, which spreads the photons out even more. They cross this interface. There's a little bit of spreading there, adding noise, passes through a fiber optic stub, adding noise again, another interface, and finally detected by a silicon sensor. The photon energy is now preserved and the signal is spread out. And it's actually spread out in a very long tail function, a Gaussian with Lorentzian tails, which adds noise as well. In an HPC detector with direct detection, the X-ray photon comes in, it's absorbed in a single pixel or maybe 2 pixels, and read out. So here we have a very large signal. It's converted to a digital signal through discrimination, and very, very little noise is added. Here we see. And so here is that spreading of the signal due to the various sources of noise in an integrating detector versus a photon counting detector. So one of the other important features of the hybrid photon counting technology, which has actually been adopted by other vendors now, is something we have called zero dead time mode. And basically this mode allows us, through the use of 2 counters at each pixel, to acquire data and read at the same time. So we're flipping between counters, which allows us to have a dead time between reads of each pixel on the order of just a few nanoseconds, much, much faster than typical exposure rates in a home lab experiment. A standard mode for an older detector or an integrating detector is acquire, read. And so over the course of the experiment, you actually have quite a bit of accumulated dead time. So our newest detector is the HiPix Arc 150, and this derives from the idea that cylindrical detectors have a number of advantages in the diffraction experiment. Obviously, a spherical detector would be ideal. we don't have that, and we probably won't for some time. So the original cylindrical detector, for many of you who might remember, is the original Weissenberg, originally developed in 1924 to simplify the interpretation of diffraction data. And until the end of point detector serial diffractometers, curved photographic film was actually very common, and we also had curved image plates. So the HiPix arc provides the ability to surround the crystal up to 150 degrees with detection surface. It's the latest addition to the HiPix family, as I mentioned. It continues to use HPC direct detection technology, maintains 100 micron pixel size, and has race technology for frame rates up to 70 hertz. So some of the important features of a curved detector I've alluded to, but I'll go through in more detail here. All reflections are collected under the same conditions. So we can collect low 2 theta and high 2 theta reflections at the same time. You see with a curved detector, we have up to 150 degrees in a single exposure. We get minimum distortion, and this allows to collect data more quickly. And I'll go through some of the other important features on the next slide. So I mentioned reflection distortion. So with the curved detector, we preserve the shape of the reflection better versus a flat detector. So the oblique incidence on a flat detector will cause the spreading out of the reflection. And so that adds noise because you have more background to contend with. On a flat detector, we also see parallax within the detector. So once it hits, the X-ray photons hit the detector, or the sum of the reflection hits the detector, it gets spread out as well inside the detector because the detector is not zero thickness. And so that is reduced again, improving signal to noise in the curved detector. So with a curved detector, we can also achieve higher angular coverage with a smaller surface area. And so this is shown graphically here. I was going to say diagrammatically, but I'll just say graphically, fewer syllables. And so for the X-ray beam hitting the crystal, we see this cone of diffraction that is actually accessible to the curved detector that is not available to the flat detector. And so you have the peak as seen by the detector, X-ray beams in and out, the sample obviously, and then our extra diffraction. And so as a result, there are fewer corrections. We don't have to have scan speed scaling, lower dose, lower sample decay, fewer exposures to scale together, less random noise. So those are some of the improvements that the detector provides. I also wanted to point out that one can collect IUCR resolution data in one setting of the detector. It's trivial to collect MOLI IUCR resolution data. And furthermore, it becomes much easier to collect charge density data, quantum crystallography data with a detector with such a large coverage area. So just a quick comparison, HiPix arc here, curved detector versus the flat HiPix 6000. Pixel size same, one can use the same sort of source. Hybrid photon counting, we have much larger area. The only compromise in performance is the HiPix arc has 70 hertz of maximum frame rate versus 100 hertz for the HiPix 6000. So Mark collected some Thaumatin data comparing the HiPix arc and HiPix 6000, and he collected crystals first on the arc, swapped the detector, realigned the goniometer, collected on the HiPix 6000, and used a strategy to target the same redundancy and resolution on the arc and collect the same overall exposure time. And so here is an example. You can see it's essentially the same crystal on the arc. The lighting was different between the two, so this looks a little bit more yellow. You can see the enlarged area of collection of the arc compared to the HiPIC 6000. Mark collected data for approximately 2 hours, both at 45 millimeters. And remember, I mentioned that rule of thumb being, instead of 1 angstrom, 1 millimeter per angstrom, it's approximately 1/3 millimeter per angstrom. So in both cases, he's collected at 45 millimeters. And so here are some results. With the HiPIC's ARC, Mark collected data all the way out to 1.45 angstroms versus 1.75 angstroms. So here's an example where the extra module that gives us the curvature of the detector gives us substantially more data in the same amount of time. So Rigaku supports additional detectors. We still support the HiPIC's, the Pilatus 300K and cadmium telluride, as well as other Pilatus detectors. We also support the Eiger and the Eiger 2 detectors in 1M and 4M formats. Moving back towards the source, we have the 4-circle kappa goniometer, which supports the crystal, omega, phi, and kappa, as well as the detector with 2 theta and distance. Chrysalis Pro provides an intelligent strategy with forward and reverse scans to minimize drive time, as well as faster motor speeds to enhance throughput. So moving back further, we'll talk about modern X-ray generators and optics. So microfocus seal tube source have been used for a couple of decades now in the home lab. Very robust, very reliable. Multi-layer confocal optics provide very good throughput with these sources. Smaller spot optics means higher performance even though low power is used. Water cooling is still used to achieve the best thermal stability in these systems. So how do we get more power out of these systems? Well, a lot of you are rotating anode customers. I can see from the list of users. Some are still microfocus seal tube source customers. So the way we get more power is we rotate the anode so that we can dump heat and allow the anode to cool as it's spinning here. And so this allows us to go from 50 watts to all the way up to 3,000, nearly 3,000 watts, 2,975 watts in the case of the FRX and 1,200 watts in the case of the 007 HF. So we're always improving our rotating anodes. In the Synergy R and Synergy DW, we have reduced the power requirement to single phase, which reduces the means that we have lower energy consumption and allows for simpler installation. The Synergy R systems and Synergy DW systems have the anode bolted directly to the goniometer base. This gives a much higher stability for the system. And as I said, we're always improving the rotating anode. So this is a Photon Jet R compared to what we have found in the literature for a diamond tube with high divergence optic versus the competitor's 1 kilowatt rotating anode. You see that our implementation of rotating anode technology is better than our competitors. We've been doing it much, much longer. So in terms of continuing the improvement of the rotating anode, here is an example of the FRX versus pinhole size, with the smallest number being 25 microns, 50 microns, 100 microns, and so on. The FRX provides the highest performance of any home laboratory source. So in terms of servicing, we have a world-class service department here in the US, in Europe, and in Japan. Scheduled service is comparable to seal tubes, which is about 1% of downtime. And we have an anode exchange program that greatly simplifies the anode maintenance for annual anode maintenance for your system. So what can a rotating anode do for you? Well, you can do more research, faster experiments, more challenging samples, and smaller crystals. And so here's another example, again from Mark, who's taken a lysozyme crystal with sucrose bound. It turns out that this provides a very high resolution data set with a high pixarc. You'll notice this last resolution arc here is at 0.83 angstroms. It was a big crystal, obviously, but Mark was able to collect data in about 2 hours. And I'd also like to comment that this was actually a slow data set. Mark has a data set in 33 minutes to 0.85 angstroms on a different crystal. Mark process this data both with Chrysalis Pro and XDS, and we find, in fact, with Chrysalis Pro, much better signal to noise. The I over sigma is almost 2.5 times, or more than 2.5 times that of the XDS process data. So we're exploring that as well. Data to 0.83 angstroms, and beautiful maps showing the sucrose bound atomic resolution. Obviously, Mark is currently refining this with Shell Excel, and we'll deposit this into PDB as the highest resolution lysozyme data set. Without sucrose bound, we have a 0.97 angstrom structure, and we clearly see ethylene glycol in the same pocket. So I mentioned small, that was a gigantic crystal. So I mentioned smaller crystals. So here's an example of a very small crystal where we've looked at it with the, well, a large version of this particular sample, and then moving down in size till we get to 50 by 40 by 6 microns. So these are difficult or almost impossible at best with a microfocus seal tube source, but possible with a rotating anode. And so considering a volume of 1 to a volume of 0005 here, the rotating anode allows you to do experiments that you can't do with a seal tube source. And so in the ultimate experiment, we wanted to look at how to run samples that were almost as small as the maximum size for a microelectron diffraction experiment. Remember, for micro-ED, your thickness can't be really much more than 500 nanometers for a organic sample, and smaller even for a inorganic sample. So here we have a 3 by 2 by 1 micron crystal that's been pulled out of an Excedrin capsule. This is an Excedrin capsule from a pharmacy in Japan. Data were collected in about 34 minutes. A very nice R1. The hydrogens can be found from the difference Fourier map, which is also quite good. And note the smallest dimension of this crystal is 1,000 nanometers, or just twice what the largest would be for a micro-ED experiment. So just a quick comparison between a Synergy S microfocus seal tube source and a Synergy R. We can collect data significantly faster. The dose time here is about a factor of 6 better with the Synergy R versus the Synergy S. And this was, again, a small crystal, similar I over sigma, similar R-ints and R1s. So I was going to talk a little bit about the Synergy R. Highest flux compact system for challenging projects. The Synergy R fits completely within the standard Synergy cabinet, very compact. Obviously, your low temperature system will take up some space to the outside. This has an external chiller, but still runs on single phase. This improves on the 007 rotating anode technology, 1.2 kilowatt generator with purpose design, high performance multi-layer optics. The entire system is software controlled and monitored. A recent addition to the Synergy line includes the Synergy DW. You may have seen this introduced in the Rigaku newsletter that went out this morning. We have a Synergy 007 DW source here, copper moly. Could be moly silver, could be other combinations as well. Very high flux DW optic, and then the Synergy system here. And so then we move to the Synergy Customs, which include the dual port option of the 007 or the FRX. This is an FRX, the most high brilliance source out there today. This is shown with an HF optic and a Synergy goniometer with a HiPix 6000. Everything is software controlled, low maintenance. Rebuilds are typically about 1 year with the system and dual port capability. So you have the ability to put a second system here for single crystal, or a SAC system, for example, on that left port. Just a quick review, the 007 operates at 1.2 kilowatts, while the FRX operates at 2.975 kilowatts. So another important feature of the Rigaku systems are the variable divergence slits. X-rays are focused on the sample to achieve maximum flux. Then we can trim the beam to provide the ability to resolve large unit cells. So here is a 50S ribosomal subunit. Here we're tuning the divergence so that we can resolve these reflections. Obviously, the flux will go down. We don't get nothing for free per Louisville's theorem. And so the flux goes down, but we are able to resolve these reflections clearly. The other advantage of this is that you can use it, for example, improving resolution in powder experiments. So Actor is one of the options that we have for the Synergy Custom systems. Here it's shown on a legacy AFC 11, but now works with the Synergy goniometers. We have a couple of these installed in the field now. And so this is the safest and most reliable system, fully hands-free. We provide lots of flexibility options. New doer options support up to 112 samples. And in addition to being supported with the universal goniometer and a Synergy Custom systems, it's supported by Chrysalis Pro. So the main components of the Actor system are the robotic arm with the cryo-tolerant end effector. This is a Gen 4 end effector, continuous development. Ice-free staging doer, motorized XYZ goniometer head, laser, and in-doer pin sensors. This prevents collisions and the like. Cryosystem retractor, end effector drying station. So in terms of additional options, we have barcode tracking, fast dry, which allows you to dry in as fast as 22 seconds. And a second camera is an option for faster centering. So another option that we have is we can provide in situ diffraction capabilities, and in situ crystallography provides for rapid identification of protein crystals. You can avoid taking salt or detergent to the synchrotron, quickly establish diffraction quality of crystals. Crystals are in fact suitable for data collection. We've collected data on a number of samples in the wells and merge the data and get reasonable results. You can go back to the bench and optimize the experiment. You don't have to take the crystals out of the environment, and you avoid crystal damage. So here is the Xtalcheck-S as shown on a universal goniometer, the kappa tucked away out of the harm of collision, and you can collect data. In this particular setup, we actually have a second camera here pointing at the crystal for proper centering. In a standard Synergy setup, the camera is looking down on the crystal from here. You can also see that this would be the setup one would use with Actor to speed centering. You can access all 96 wells without having to flip the plate. It supports most SBS formats, and we have object selection and queuing experiments is performed through the Chrysalis Pro interface, and we can even input comma-separated value files from other imaging systems and use that to go directly to the crystal. The last thing I wanted to mention before we do our next poll is the Chrysalis Pro, which allows one to do both small molecule and protein data collection very quickly, very intelligently. typical experiments can be done very quickly in just a few minutes. Experiments for connectivity can be done in a minute or less sometimes. And so this is a very powerful package. It can be used for protein, small molecule, actor, in situ crystallography. Everything works with our modern systems through Chrysalis Pro. And so Fraser has our last poll here.
Thanks, Joe. So as many of you are biological crystallographers, we'd like to know what software you're using for processing your data. So I've launched the poll now, so feel free to vote. We have several options here: Chrysalis, Dials from the Diamond Light Source, HKL, iMOSFilm, and XDS. So I'll give you another half a minute or so to answer this one, and then I'll share the results. So far,
we'd like to get at least 50% of you voting. And as I mentioned earlier, you can vote anonymously. A couple more people. Okay. Why don't we go ahead and close it, Fraser?
Yeah, and here are the results.
All right, thank you. So about 53% of you are using Chrysalis Pro. 27% of you are using XDS. So we probably have a self-selected group here, being a Rigaku webinar. It's interesting, being a European webinar, that so few people are using Dials and iMOSFilm. Very interesting. Thank you. Okay, so in summary, what the new systems from Rigaku provide is the ability to maintain throughput via redundant systems, provides for better integration, and I don't mean of your data, but that happens too, but the entire system, higher performance, better productivity, less time on publication problems, more research targets, smaller crystals, more difficult targets, and the ability to do crystallography interactively. For example, structure-based drug design, a very quick experiment to tell the chemist how their ligand has bound to the target, or if it's actually bound to the target in the right place, and a very useful information. And with that, I'll thank you and remind you that you can contact us at Rigaku, either here in the Woodlands or in Europe or Japan. So we'll open the floor to questions and answers.
So please ask your questions through the Q&A feature, and I will read them out for Joe. If you don't know where that is, maybe if you go to the bottom of your screen, you'll see the Q&A option down here. I have one question for you just now, Joe.
Sure.
So we've seen that the high-pitch detector has a 100 Hertz frame rate. Why is this useful when my exposure times are often several seconds or even minutes?
It depends on what the count rate that you're seeing. So if they're very weak crystals, the exposure time will go down to 1 Hertz or even less. It's automatically determined by the diffraction quality of the sample. A fast frame rate is useful when you have very high count rates. When you do the count rate correction, you want to sample, you want to have as many samples as possible so that at each point along the peak, your count rate is adequately corrected for. If you do a slow count rate correction on a peak like that, you're going to get the average, and so you will get underestimation of the total rate. So
so the next question we have, for multi-wavelength source, do you have multiple optics?
We do. So let me go back a few slides. So if you look carefully, let me get my pointer working. Inside here, you can see two L-shaped pieces. And so each one of those is an optic. In this case, we would have one, let's say, for moly and one for copper. And the optics rotate in the housing like or the cylinder in a revolver. And so we've also designed this so that each optic is floating on its own alignment stage. And these knobs here are engaged when an optic is in position for alignment and disengaged when the optic is in use or when it's being rotated. So that allows us to align both optics independently and then be able to rotate them and reproduce that alignment every time you change wavelength. And the wavelength is changed here by moving the anode back and forth across the seal, so across this gland seal here, and that allows us to, again, switch wavelengths without realignment.
Okay. The next question is, what's the minimum beam size for the FRX?
The FRX minimum beam size is approximately 100 microns full width at half maximum.
Okay. So we have a clarification request here. In your summary, what did you mean by maintaining throughput via redundant systems?
Well, you know, at my house, I have electricity coming in from the power grid, and I also have an emergency generator. And on that emergency generator, I can run it with either gasoline or propane. And so by redundant systems, I mean that if you don't have access to your synchrotron, you still have the ability to collect data in your home lab.
Another question is about maintenance. So how much downtime is expected throughout the year with a rotating anode?
With the rotating anode, less than 1%. There will be a filament change 3, 4, 5, 6 months. It'll depend on how you use your system. We feel that protein crystallographers generally run their system 24/7, so filament changes will be on the order of 3 to 4 months. The anode rebuild is approximately once a year. And so that results in desk times less than 1%.
So there's a question here related to an earlier one. Does the beam size change with the wavelength?
It does. And the reason the beam size changes with the wavelength is that the optics are different and the optics see a different source based on the wavelength. And so for copper, the beam size is about 25% larger than it is for moly.
Okay, I think that's all the questions that have come in so far. So
were there any in the chat window?
I don't see them there. I think, yeah, I think we're done.
Okay.
Questions. If anyone has any more questions, we can stick around for another few minutes while you ask them. Otherwise, thank you very much for attending. I think that's all we've really got time for, and we'd like to thank you for taking the time out to join us. We hope you found the webinar useful, and please check the www.rigaku.com/webinars website regularly, as there will be updates to the webinars going up there periodically over the next few weeks and months. So lastly, we hope you're all staying safe during this difficult time, and we wish you a pleasant rest of your day. Goodbye.